Hello, this is Mr. P, and today we're going to continue with our study of the conic sections by looking at the geometric interpretations of the hyperbolas. As we saw with the ellipse, the definition of the ellipse was the set of all points where the sum of the distances to two fixed points where they're constant. And for the hyperbola, we're going to look at the same idea. We have two foci, but this time the difference between the 2 points is going to be constant. So looking at our model here, and this is a vertical model, this point that is on the graph xy, you have D1 goes to one focus, D2 goes to another focus. The difference between those two are going to be the same for any point on that graph. Now our terminology does change a little bit from the ellipse to the hyperbola. And what we used to refer to as the major axis, which in this case is going to be straight up and down. We refer to it as the transverse axis when we're talking about the hyperbola. So it's a major axis for the ellipse, transverse axis for the hyperbola. It is going to be the line that includes the center, both of the vertices, and both of the foci. Notice also how the foci in the hyperbola are further away from the center than the vertices are, where that was the other way around with the ellipse. And then along with, if we look at our horizontal model, this would be our transverse axis, and along with that, the axis in the other direction, which was called the minor axis for the ellipse, is called the conjugate axis for the hyperbola. And we still have the same idea of the distance from the center to the vertex, or in this model from the center to the vertex. That distance is going to be A, just like it was in the ellipse. And the distance from the center to the foci is going to be C. But unlike the ellipse, which had A being the largest value, in the hyperbola, C is always going to be the largest value. So when we look at that hidden triangle, C is going to take on the role of the hypotenuse rather than A being the hypotenuse. So A is center to the vertice. C is the center to the focus, which would be out here. And then B is from the center to the end of the conjugate axis. And the easiest way to graph these is once you know that distance B and you know the distance A, you use those to make a box that includes both vertices and both ends of the conjugate axis. And once you have that box, you draw your asymptotes through the corners of that box. Sometimes the box will be square, sometimes the box will be rectangle, but you'll draw the asymptotes through the corner, and then from the vertice you'll approach the asymptote in one direction and approach the asymptote in the other direction. And you do that for both branches of the hyperbola. The other thing to know about the hyperbolas is you can find the equation of this asymptote by using these models. And what you want to pay attention to is the B over A part. Notice how, and I'll even show you a little with the highlighter here, notice how we could have drawn this triangle, and then this side still would have been B, although that's a little tough to see. This side still would have been B because this distance is the same as this distance. And this distance is also going to be C as well. So we could have drawn the triangle this way, or we can draw the triangle this way. So you can see B is also the distance from the vertice to the asymptote as well. And when we draw the triangle this way, it's actually easier to see that the slope of this line is going to be rise over run, which is why it's B over A. So for the horizontal model, you're going to have B is going to be your rise, A is going to be your run, so it's B over A. In the vertical model, when you draw it out, it's going to be A is actually your vertical distance, and B is going to be your horizontal distance. So looking at our models here, the horizontal model is the exact same thing as the ellipse model, except it has a minus instead of a plus. With the ellipse model, we would flip-flop the A and the B position back and forth to differentiate between a vertical and horizontal model. However, with the hyperbola, the A and B are going to stay where they are, and the A still represents from center to vertice, and the flip-flop actually occurs with the X's and the Y's, and it's the entire parenthesis. Notice how the H stays with the X and the K stays with the Y, but since we have subtraction, the order of the subtraction is what matters. So if you subtract two things and the result is a positive number, that means that first thing was larger. So if it begins with an X, that means X is larger. That's what makes it horizontal. Excuse me. And if it begins with the Y, then the Y was larger, and that's what makes it vertical. That's the easiest way to differentiate between the two models. And of course, if H and K are both 0, if the center is at the origin, then you will have these more simplified versions of the equations. All right, so let's look at the skills we need for this. We're going to find the standard equation of a hyperbola, and they give us that the foci are at these coordinates and the vertices are at these coordinates. And the first thing to realize is, just like the ellipse, the hyperbola does have the symmetry where both of the foci are equally spaced about the center, and likewise the vertices are equally spaced about the center. So using the midpoint formula, you can easily find, and you can use either pair, you can easily find that the center is 2, 2, which means we immediately know H and K. H will be 2, K will be 2. And then, since they're evenly spaced, we see the distance from one foci to the other. The only thing that changes is the X values. So this is going to be a horizontal model. And you can see to go from -1 to 5 would be a distance of 6. So half of that distance would be from the center to a foci, which is how we get the value of 3 for for C. So C, being the distance from center to foci, is going to be 3, which is half of the distance from foci to foci. Likewise for the vertices, which the distance from center to vertice is A, we have from vertice to vertice is going to be 0 to 4 is going to be 4 units, and half of that is 2, so A, the distance from the center to the vertex, is going to be 2 units. Once I know A and I know C, we can do the Pythagorean theorem. Just make sure you use C as in the role of hypotenuse, and then if you calculate correctly, you should get square root of 5. So now we know A, B, C, H, and K, and we can answer any of the questions they want us to. And they want us to find the standard form of the equation. So to do that, we're going to take our model, which is the horizontal model. So the X comes first. And then our A was 2, that goes right here. Our B was square root of 5, that goes here. And then the H and the K was where we get the -2 and the -2. Remember, H and K, or in other words, the coordinates of the center, they represent the values of X that cause this to be 0 and the value of Y that causes this to be 0. So it's +2 and +2. So therefore our answer does make sense. Now let's look at, of course, one more example. I'll give you an additional example here. And we're going to find the equation of this hyperbola. And although they don't tell you to draw the picture, I still like to do that. I like to see the visualization. So here we have foci at 0, 0, and 8, 0, vertices at 3, 0, and 5, 0. Notice the only change here is to the X components. So once again, we're going to have a horizontal model. So I like to identify that right off the bat. This is going to be our model, the one with the X coming first. And now if we sort of think about how these would lay out, if we sort of look at a visualization of this, one foci is at 0, 0. The other one would be all the way over here at 8, 0. So halfway between there would be the center, which would be at 4, 0. And then a focus at 3, 0. And a focus at 5, 0 would be between those 3 dots. So that's how our transverse axis would lay out. And then this distance from foci to the center, which is c, that is going to be the same as the hypotenuse. And we know going from 0 to 4, we're going to say c is 4. From here we can, of course, find our h and our k is our center. And we can find c is 4, the distance from here to here. And a would be 1, the distance from center to a vertex. So a is 1, c is 4. Once I know those two, I can do the Pythagorean theorem, treating c as the hypotenuse, and I get square root of 15 for the length of b. So now we know a, b, c, h, k. We know everything we need to know to plug into the model. And when we make those substitutions, we get this. And cleaning it up just a little bit, I can say that, well, 1 squared is 1, and root 15 squared is 15. So that would be our equation. Now, sometimes you have to do a little manipulation algebraically when you're given the equation and in general form. So looking at the general form, we need to complete the square for the x and complete the square for the y. So when we do that, we're going to group the x's. We're going to group the y's, but there's only one of them. And then for the x's, I will need to complete the square because there's no linear term for the y, so I can sort of leave it as it is. But before I complete the x's, I do need to factor out that leading coefficient. So I factor out the 4, so 4x squared becomes x squared, and 8x becomes 2x. So I have that 4 on the outside. Now when I complete the square, I of course divide by 2 and square it, which gives me 1. But the net change is not just 1, it's 4 times 1, which is what I add on the right side to keep equality, to keep the equation balanced. And now I can factor the perfect square trinomial, and then I can combine like terms, and then whatever this number is on the right, I'm going to divide through by that number because I know the right hand side of the equation must be a positive 1. So dividing through by negative 12 allows me actually to change the order here, because notice how the negative y squared was going to become positive and the positive x is going to become negative. So I changed the order so I can write it as y squared minus x squared basically. And dividing through by the 12, 4/12, 4 over 12 is going to reduce to 1/3, and I can write that as square root of 3 squared. And then 3 over 12 is 1/4, which I can write as 2 squared. So therefore everything's in standard form. From this I can pick out all the information I need, and the paragraph will explain a lot of it, but the easiest way for me is they do want us to sketch the hyperbola, so the easiest way for me is to start with the center. So our center is going to be negative 1, the value of x that causes that to be 0, and 0. So negative 1, 0, that's going to be my center. And then from there, I'm going to look at my distance, my distance to the vertex is going to be 2. So from there, I'm going to go up 2 and down 2 because it's associated with the y value. So up and down 2 units, I would make those dots. And then in the other direction, I'm going to go square root of 3 units, which is approximately 1.7. So from here, I go about 1.7 this way, about 1.7 this way, and I would make a light little dot there so that I can create this box. Creating the box would be the first thing I would do. And then through the corners of the box, I can then make the asymptotes. Once I have those and I have my location of the vertex, then from the vertex I can approach the asymptote in that direction, approach the asymptote in that direction, and same thing on the bottom. I find that's the easiest way to sketch these, is figure out your center, and then figure out your A and your B so you can create the box. Once you have the box, you create the asymptotes, and then from the vertex you're going to approach the asymptotes in either direction. Now they did also ask for the equation of the asymptote, and we can just use our model. We have in the vertical model here, notice how the rise is going to be A is your rise, and the B is your run for the slope of that line. So this time it's A over B rather than B over A, and everything else fits into the model. All right, let's look at an additional example of that. Again, we're given this equation. We are going to group the y values because the x value doesn't have any linears, so we're going to group the y values. But then whatever the leading coefficient is, if the squared term has a coefficient, we're going to factor that out, which includes the negative. So I'm going to factor out a -4, which makes the squared term just y squared, but then positive 8y becomes -2y when you divide out -4. Now again, we're going to complete the square by taking the linear coefficient, divide by 2 and square it, get +1. And then this is where you have to be careful. This is where I see a lot of mistakes. So I put 1 here, and it's not just 4 times 1 that I put over here, it's -4 times 1 gives me the -4. So now I preserved equality. And now it's just a matter of cleaning up a little bit, combine like terms, factor that as a perfect square, and then divide through by whatever this number is, and that will give me this equation when I write them as squares on the bottom. So that's my standard form. And from this I can look at h is going to be 0, k is going to be 1. In other words, the value of y that causes that to be 0. My a is going to be 2 and my b is going to be 3. So I know a, b, h, and k right off the bat. And graphing, I start with h and k. I start with the center. So 0, 1, that's my center. I make that dot. And then since this is associated with the x value, the horizontal, so the x comes first. So in the horizontal direction, I'm going to go 2 units from the center in either direction and make a dot. And then in the y direction from the center, I'm going to go up and down 3 units. So up 3 units, make a dot, down 3 units, make a dot. And then I can use that to make my box. It's the rectangle that includes all 4 of those points. Once I make the box, and notice I am making them with a dotted line because these are not actually on the graph, so they should be dotted lines. Once you make the box, then you're going to draw, again, dotted lines for the asymptotes through the 2 corners of the box. And now you have everything to make your graph. From the vertex, I'm going to approach the asymptote in that direction, approach the asymptote in that direction, and I'll do that for both branches. And then, of course, they also wanted the equation of the asymptote. So I'm going to use the formula that's given to us in the notes. Notice how it's b over a, because the a is now your run and the b is your rise. So the slope is b over a. That's the only thing that changes in here from horizontal to vertical. And when I substitute in the values I know, I get these are my 2 equations for the asymptotes. Y equals 1 plus 3/2 x, or y equals 1 minus 3/2 x. Alright, the final thing we're going to look at is being able to recognize which type of conic section you have just by looking at the equation. So this is the general form for all conic sections. The A, B, C, D, E, and F, those are just the coefficients of this big general equation. Now, we've been dealing with equations that do not have this term, the bxy term, and that comes up in the next section actually. The bxy term is what we'll call as a rotation of these. Everything we've been dealing with so far has been just horizontal or vertical, but with the bxy term in there, they can create rotations as well. So ignoring that term for our purposes today, we're going to look at how to classify these equations. So first of all, we look at the coefficients of the squared terms. Those 2 coefficients can tell us everything. If they are the same coefficient, the exact same number, then you're going to have a circle. In other words, if A equals C, you have a circle. If they are, if one of them is missing, in other words, if one of them is 0, if you have an x squared term but you don't have a y squared term, or vice versa, then that means the product will be 0, but not both of them 0. You have to have one but not the other. If that's the case, then you will have a parabola, because then, in effect, the equation is basically y equals x squared or x equals y squared. So that will be a parabola. If they have the same sign, if A and C have the same signs, but different values, then that will be an ellipse. In other words, A times C is positive. That means they have like signs, so that is going to be an ellipse. And technically, even if they have the same value, a circle is a special type of ellipse, so technically it does work if they have the same value. So if they're either both positive or both negative, then you have an ellipse. And if one is positive and one is negative, that means the product would be negative, so you would have a hyperbola. So looking at these real quick, you should be able to classify them. So here we have an x squared, but we don't have a y squared. Or in other words, A times C would be 0, which means we have a parabola. The second one, when I look at it, I see a positive x squared, I see a negative y squared. They have different signs. In other words, A times C would be negative, and that makes it a hyperbola. The next one, they have the same sign, so therefore A times C is going to be positive, and that gives us an ellipse. And the last one, they have the same sign, but they're also the same number, which makes it a special type of an ellipse. So A equals C, and therefore we have a circle. And of course, I'll give you a couple extra examples. If you want to pause and try to do these yourself real quick, you can do that. But running through them, we have, here we have, for part A, we have different signs. Therefore, I should know right off the bat I have a hyperbola. Here, both coefficients are 1, positive 1, so I'm going to have a circle. Here I have an x squared, but I don't have a y squared, so that's going to be a parabola. And finally, I have both of them are positive, so that is going to make an ellipse. Both are positive, but not the same value, so it's an ellipse, not a circle. Alright, and with that, we are done.